Right, having done the first video where I tell you how we can use the rules for logs and exponentials, I want to spend a little bit of time now going over the situations where we'll use logs and exponentials, particularly in physics lessons. Just by quick reminder here, that was how we finished the video previously. So if you want to do so here, just make sure that you're confident with these ones here. So log of a times b as log of a plus log of b. Log of a squared is 2 log of a. Log of 1 over a is just minus log of a. Log of a over b is equal to the log of a minus the log of b. And log of a b to the power 4 is log of a plus 4 times the log of b. And this bottom one here, which again is quite important, the log of e to the power x just is x itself. Log and e are inverse functions of each other. So, use of exponentials and logs in physics. There are 3 main ways, and you need to be confident with all of these three main ways in which we use logs and exponentials in physics. And these are, first of all, if you have some exponential equation, whether that's to do with a capacitor discharging or radioactive decay or any other exponential behavior, you may want to rearrange the equation such that t, which is in the exponent, you make t the subject of the equation, and we'll see how we can use logs and exponentials for that. Secondly, and particularly when we're plotting graphs, if you've got an exponential function, you may want to plot a straight line graph, and again you're going to need to use logs in order to do that one. And the third one that is probably less common, but certainly is seen a number of times in the practical paper, when you've got a function of the form v is equal to k r to the power n, where n is an unknown value, then we can use logs to work out what n is, and I'll show you how to do that in a few minutes. So let's have a look at the first example. Here we've got this one here, v is equal to v naught e to the minus t over rc, the common equation for potential difference across a capacitor that is in a discharging circuit. So we want to rearrange this equation to make t the subject of the equation. Now there are a number of ways of doing it. I'm going to show you one example here, but if you do it a different way, that's absolutely fine. But what I'm going to do is first of all divide both sides by v0, and I get v over v0 is e to the minus t over rc. And then what I'm doing is I'm going to say, well, I know that log of e to the anything is just equal to the thing itself. So if I want to get rid of the e function on the right hand side, I've got to take the log of the right hand side. Obviously, if I take the log of the right hand side, I've also got to take the log of the left hand side. So I'll end up with the log of v over v0 is equal to the log of e to the minus t over rc. And then we're using one of our rules that says the log of e to the anything is just equal to the thing itself. Now, I haven't quite got t by itself there. I've got to multiply both sides by rc first of all. And then just to finish it off, I'm going to multiply both sides by minus 1. And I'll get t is equal to minus rc of log of v over v0. So that's one way of rearranging that equation to make t the subject. And then if you know what v is at any time, and you know what v0 and rc is, you can work out how long it takes for the capacitor to fall to a particular value. So that's one way of doing it. As I say, there's a number of different ways of rearranging the equation, but you'll always end up with the same answer when you put the numbers in. Let's have a look at the second one, and this one is one hopefully that you're already familiar with. We've got the equation v equals v0 e to the minus t over rc, again an exponential function. But importantly, if we're taking readings, for example, if I was taking values of v and at various times t, then I might want to plot a graph to make sure that I get a straight line graph for this one. And from the straight line graph, I'll be able to work out what the time constant is, what the value of rc is. So the way that I do this is like this, slightly differently. I'm going to take the logs of both sides. I'm going to say log of v is equal to the log of v0 e to the minus t over rc. that I will then expand like this. So I've now got that as log of V0 plus the log of e to the minus t over rc. Again, hopefully you can spot that log of e to the anything is just the thing itself. So I get log of v is equal to log of V0 minus t over rc. Now I'm slightly going to just rearrange this equation, and hopefully you'll see why in a minute. If you look at this one here, if I just swap those two terms on the right hand side round, and then I separate out the things that don't change, that is RC, from the thing that does change, T, then I'm going to write that equation down like this, that the log of V is equal to minus 1 over RC times T plus the log of V0. So what this tells us is that if I've measured V at various times t, then I can plot the log of V on the y-axis and plot t by itself on the x-axis. If I do that, then I'll find that the gradient of the straight line graph will be minus 1 over RC. So if I can work out what the gradient is, then I can work out what the value of RC is. The value of RC will just be minus 1 over the gradient. I could actually use the value of the intercept to find out what log of V0 is, but often you don't need to do that one there. So those are two derivations there. You should, as I say at the beginning of the first video, have the handout sheet with all the notes on it. What I'd recommend you do now is, having just seen those two derivations there, see if you can do those two derivations for yourself. There's a space on the sheet for you to do that working there. See if you can do it from memory. If you feel that you need to pause this video and go back, feel free to do that one there. But I'd recommend at this point now you just pause the video and see if you can do those derivations for yourself. Let's assume you paused it now and now are going on to this one. Let's come on to the third way in which we use these equations. And as I say, this is quite commonly used in practical papers. If you're told that you've measured two variables, and you might have been told that those two variables, in this case V and R, are linked by an equation which is V is k r to the power n. But you're also told that you don't know what the value of n is. So how are we going to use logs to get the properties that you're plotting on the x and the y-axis to be either v or r, or functions of v of r or r? Well, let's start off with this way here. There's the equation there. What happens if we take the log of both sides? Well, the log of v, the left-hand side, is the log of k r to the n, that I can split up using our first rule to be log of k plus the log of r to the power n. But then I can use one of our other rules that says log of v is equal to log of k plus n lots of the log of r. Now what this tells us is that if we've taken data for v and r in this particular example, if I plot the log of v on the y-axis and the log of r on the x-axis, then we should get a straight line graph, because n we know to be a constant and k we also know to be a constant. So we should get a straight line graph there, and importantly in this example here, the gradient of the graph will be equal to the value of n. So that's the third way in which we can use logs there. So let me just link those last two together, because we love drawing straight line graphs, because you can see that the correlations fit well together and we can actually work out lots of interesting arrangements. So there are the two rearrangements that we've done, just emphasizing that what we're aiming for is to get those equations into the form y equals mx plus c. Okay, finally, just to finish off this video here, let me see if I can get you to do this mental arithmetic. I've told you here a couple of things. First of all, log of 403.4 is 6.00, and log of 6.389 is 2.00. See if you can do these without your calculator. Okay, Again, I'd recommend you pause the video at this point here, and when you've come up with the answers there, then restart the video. So let's work through these ones here. The log of 6.3589 times 403.4, well, that's just the same as log of 7.389 plus the log of 403.4, so that's just 2 plus 6, so that gives us 8. What about this one here? Well, that's giving us the second one divided by the first one, so that expands to the log of the second number take away log of the first number, so that gives you 2 minus 6, which is minus 4. This one here, log of 403.4 squared, well, that's just the same as 2 lots of log of 403.4. 2 lots of that is just equal to 12.